Hello and welcome to another lecture. Uh, this time in numerical methods for solving, in this case, we're going to solve ordinary differential equations, first order ordinary differential equations, and we're going to look at Euler's method in particular, the simplest one of all. But we're going to talk sort of more generally about numerical methods. So this is section 1.7 in the book, and you can get the book for free as a PDF at that URL, or you can buy a paperback if you want. All right. So now the idea is that, you know, generally we're given an equation, we're given initial conditions, and we'd like to find a solution. So the best solution that we can find would be a closed form solution. You know, something that we have an explicit formula for this you know, for this equation, right? Now, it's often hard to find these. Well, they actually don't always exist. It's somehow it's basically just like solving integrals, right? I mean, because integrals are just very specific ODEs, right? So you already know that you cannot find every integral as you know, in closed form, but you still might want to know the numbers, right? I mean, for an integral, I mean, a definite integral, a certain number, you might want to know that number, right? So same thing here, right? And so we want answers. We want this number, right? Or we want this function y in this case, right? We want this function. What do we do, right? Well, this is where we get numerical methods. So so we have to have you know, explicit formula for f, no parameters or anything, and we have to have you know, specific numbers for the initial condition, right? You know, exact numbers, x0 is 0 maybe, and y0 is 5, right? Something like that. They can't have variables or anything. And then, you know, maybe given some other point x1, we'd really want to find this y of x1, and this is what the numerical method gives you. It gives you a number which is supposed to be, presumably, it's equal to y of x1. Well, it doesn't quite give you y at x1. It gives you some approximation. Of course, how good of an approximation? Well, that's you know, that's tricky, right? Hopefully, it's very close, right? All right. Now, it's not ideal, but sometimes it's the best we got, because it only gives you numbers, right? Sometimes if you want to draw a graph, right? I mean, you could find this for a bunch of different x1s and connect the dots, right? So, yeah, you know, for certain you know, for certain applications, it's great, right? But it's not ideal. Why is it not ideal? I mean, first, we need to know these numbers exactly. Well, and the function, right? You know, they can't have any parameters. So if we want to know how the solution depends on a certain parameter, right? If we have some parameter in f, maybe, you know, there's something that we can tune in our problem, and we want to know how the solution depends on it. Well, you know, this you can't really do that. We have to have exactly these numbers, and then you can solve, right? Then you can find this thing. Maybe you can find this for a whole bunch of different x1s, draw a graph, but then if you tune a parameter, that means you have to plug in a bunch of different numbers into the parameter and maybe plot the function for all of those guys, and you know, see what you get. So it's you know, it takes more work to sort of figure out what is the what is the solution doing, right? So it's hard to get a qualitative understanding from a numerical solution, right? I mean, you have to basically solve it for a whole bunch of different. You have some parameters, right? You know, you're changing them. You have to plug in a whole bunch of different ones and see how, you know, how it behaves, right? Or maybe you want to figure out, you know, how quickly is something growing, right? Even as x changes, maybe you don't have any parameters, but well, you're just getting numbers, right? So you have to plot a lot of numbers and then sort of maybe say, well, maybe this is going to keep going. But you don't really know because you only know it for those specific numbers, right? So you can get some quantitative idea, but qualitatively, what is happening? It's harder to get it from a numerical solution, right? And of course, it's only approximate. So you have to understand, what the error is, and if there's a big error, if there's a small error, how far you are from the real solution. It's if you're in a very simple case, there's lots of software that is written that will give you, in vast majority of the cases, it will give you a very reasonable solution. But still, you might want to understand how far you are from the solution, and if you're even close at all, right? And you have to choose the right method. So if this is fairly simple, there's some fairly general methods that will work. If this is more complicated, or maybe you have some high order ODE or PDE, this is especially for PDEs. There's lots and lots of different methods, and they have different advantages and disadvantages. So it gets very complicated to choose which method to use. Right. We're right now only going to worry about this first order ODE, and we're actually only going to worry about one specific method, the Euler's method, which is the simplest one. But a lot of the ODE ones are very similar. All right. So that's what we're doing. We're covering one method, right? But it sort of gives you the idea of what numerical methods, how do they work? What happens with them. All right, so let's see, how would we use it, right? So let's first go through in general, and then we're going to do an example, right? So suppose that we have this problem, right? So what we do is we're going to pick a step size, right? So we're going to keep stepping in the x direction by h. We're going to keep adding h to x. So we're going to get a whole bunch of different x's, and h is presumably small. Right. I mean, I might want to go from maybe x naught is let's say 0, and I might want to figure out what the value is at 2. That's actually what we're going to do in the example, right? Well, having the step size be 2 is not going to give you a good approximation. You're going to have small step size. Maybe a step size of 0.1 might give you a reasonable answer. So we'll see what we'll talk more about that. But right now, just pick a step size, presumably small, but it could be big. At this point, anything, right? Any positive number, right? Now we're at the point on the plane, right? We're basically trying to draw a graph of y, of the solution, right? So the graph is going to go through the point x naught, y naught, right? The graph to the solution. So, and we know what the slope of the solution is going to be at that point. It's whatever the value of f is, right? That's what y prime. Y prime is the slope, right? So let's compute it. Let's call it k for a moment, right? Now we're going to, draw a line, a straight line of slope k, starting at this point, right? Starting at x naught, y naught. And we're going to go from x naught to x naught plus h. And we're going to draw that graph until x gets to x naught plus h, right? And then we get a new point, right? Where we end up at x1, y1, right? Which hopefully is close to to the graph of the solution, approximately on the graph of the solution. That's what we're hoping for, right? So x1 is just, well, we add h, right? We're stepping by h. We're doing equal steps, and they're all h, right? Now y1, well, it's supposed to move, so the rise over run is the slope, right? So if I multiply it by the run, which is h, I get where y should be. So y1 will be the y at the end point of this little line segment. All right. And now we just keep repeating. So we compute the slope at this new point, and we compute x2 and y2, right? In the same way, right? So with this new k, right? And, then we compute the slope at x2, y2, right? And we let x3 be x2 plus h, and y3 be y2 plus h times k. Just keep doing the same thing. So you just rinse and repeat, however many times until the x becomes whatever you want it to be, right? Wherever you were trying to, whatever y of whatever you were trying to compute, right? All right. So essentially, the idea is that it's going to be a bunch of steps, however many, if you make little, if h is small, you're going to have to make a lot of steps. If h is big, make fewer steps. But in each step, you compute the new x and y in this way, right? The next x is just you add h, and the next y is you take h times the slope at the current point, right? Plus the old y, right? All right. So let's do an example. It's always easier to do an example. Let's do a simple one because we're going to just do it explicitly. I said h is usually small, so here it's pretty big. And we're going to start at 0, 1, right? And this is going to be a fairly easy easy function, easy equation, right? So y prime is y squared over 3. The over 3 is just to make it sort of, it doesn't, doesn't blow up too much. Anyway, it's just something that I picked. All right. So first we start at this x naught, y naught. That's this point here that I've marked, right? And here I've also drawn the slope field that we talked about, right, for this equation. And really what we're going to try to do is we're going to try to approximate, I'm going to try to get to 2. So I'm going to do 2 steps here. I'm going to go x naught is going to be 0, then it's going to be 1, and then it's going to be 2, right? And I'm going to try to figure out what is the y at 2, right? All right. Well, so I look at the slope at 0, 1, right? So that's this, slope of this sort of line over here. And you can see, well, you just plug in 0, 1 into this. So there's no x, so you're really just plugging in plugging into y, which is 1, right? So y 1 squared over 3, 1/3, right? There's a slope line of slope 1/3, right? And so then you compute x1, which is 1, and you compute y1, which is 1.3333, all the way to infinity, 4/3, right? And so the new point is over here, right? So now we're at x1, y1, right? And we do the same thing again, right? We plug in 1 4/3, right? We plug in this point into f to get the new slope, right? We're again going to call it k, and we get 16/27, right? And now you compute the new x, which is going to be 2, right? Just add 1 because we're, our step size is 1. And then our y2, well, we just, again, compute, we plug it into a formula again, right? So it's y1, which was 4/3, plus 1, which is the step size, times the slope, right? Okay, and we get this point over here, right? So it's x2 is 2, and y2 is 1.926 approximately, right? So it's a little bit less than 2, right? So that's the point, right? So here is, we can, I've connected the dots, right? So really we just computed these 3 points, right? So if you connect the dots, you get this sort of an idea. And that's our approximate solution. You can see that it's not really, it's probably not the best approximation. That's because this h is big, right? I mean, if you were thinking of, well, if I'm gonna follow these lines, right? These, you know, just eyeballing it, right? You should get something like this, right? I mean, that's more like it, right? I'm eyeballing it, right? So let's see what the you know, what the real solution is. Well, I knew what the real solution was, so I was a little bit cheating, right? But here is the real solution, right? In red, right? So this guy is the real solution, and this guy is the approximate solution. Again, you know, it's kind of bad because we chose one, but it also did very little work, right, to get this terrible approximation, right? But that's the idea, right? I mean, we're just sort of illustrating what's happening. Now, obviously, you want to do smaller h's, right? So let's see what happens if we do a couple of smaller h's, right? So we started with h1. So again, I've plotted. I removed the slope field so that it's less cluttered. So we have the real solution over here, and here's the approximate solution, and this is what we got for h equals 1, right? So you know, a common thing to do is when you have this interval h, when the step size h, is that you keep halving it, right? Because that's sort of, you know, that's easy thing to do, right? So because if you halve the interval, right? I mean, we're half the step size, right? If we want to get to 2, right, we basically just, you know, double the number of steps, right? So okay, so that's what we're gonna do. We're gonna keep halving the h, right? So first, it's gonna be 1/2. So there's 4 steps, right? We get 4 points. Well, the original, well, 5 points. We get 4 new points, right? So we start at the initial points, and then we have x1, y1, x2, y2, x3, y3, and x4, y4, right? And if I connect them, right, I get this thing, right? It's a little bit more work. You can also see that it's. Let me get rid of the highlighting. Yep. So you can see that it is better, right? Yeah, it's definitely closer to the real solution, right? Now let's do 1/4. Let's halve it, you know, halve it again, right? So if you have 1/4, I'm gonna do 8 steps, right? So I'm gonna compute 8 new points after the initial one, and you can see that we got closer, right? Again, you know, this was 4 steps. This is 8 steps, right? So this is h equals 1/4, right? We're definitely getting closer. You know, this is a much better approximation, right? So let's do 1/8, right? Now 1/8 is 16 steps, right? Yeah, and we're definitely getting a better approximation. And then how about a 16th, right? So double the number of steps again. So it's going to be 32 steps, right? 32 new points to compute, right? So, you know, what I did on the previous slide was 2 steps. So here you'd have to do 32. So it would take a whole bunch of slides, right? So a whole bunch of computations. You probably wouldn't want to do that by hand. But the whole point here is generally you let the computer do this, right? All right. So that's 1/16, and how about let's do one more. So 1/32. So this is going to be 64 steps, right? And you can see that it's already getting quite close to the real solution, right? I mean, if you were eyeballing the slope field and just trying to sort of, you know, hand draw a solution, you wouldn't do probably this good, right? So yeah, so this is, you know, it's not quite the real solution. I mean, you can see that at x equals 2, there is a difference, but yeah, it's reasonably close, right? All right. So let's talk about let's talk about the error, right? Let's talk about how far it is. So the actual solution at x equals 2 is 3, right? That's, you know, you can actually solve that. I mean, you know, it's a nice separable equation, you know how to solve that, right? So if you solve it, you're going to find that y at 2 is 3, right? All right, now if we take the difference between this 3 and our approximation for y as 2, we call that the error. And usually we take the absolute value of this difference because, generally we don't know in which direction it goes. So, it really doesn't make sense to talk about, sign of this error. So we're going to take the absolute value. How far, we don't know in which direction, how far it is, right? And that's what's called the error, right? So, for example, with h equals 1, then, we want to figure out y at 2, right? So it was x2 that was equal to 2, right? The second, second point when we were, when we were, working through Eulers. So we look at y2, right? Which is going to be y of 2, right? And we get that it's, well, I rounded here, so it's not quite equals, right? But okay, so it's, y2 is up to, 3 decimal digits. It's 1.926, right? So the error is the difference between 3 and this y2, right? And the absolute value of that. And that's 1.073 approximately, which again, rounded, right? Here the absolute value wouldn't really do anything, right? But, it doesn't really matter if you write it y2 minus 3 or 3 minus y2, right? Okay. So what about the next, next time we did, was the step size being a half, right? So there, to get to, for x to go all the way to 2, we needed to do 4 steps, right? So we need to look at x4, right? X4 is going to be 2, right? We need to add 1/2 precisely 4 times to get from 0 to 2, right? So that means that our approximation for y2 is going to be our y4, right? And what one gets is 2.209, right? Again, rounded to 3 decimal digits. So the error is, the difference of this and 3, and it's approximately this, right? Okay, so now we could, make this computation for, and I did it for more. So, like in the graphs, I get the, we went this far. So, I have the step twice more and had the computer run this, right? So this was, this over here was 1/32. So this would be 1/64th, and it's going to be 1/128, right? Yeah. So, all right, it doesn't really matter, right? But you look at, so this is the approximate y2, right? So over here we got this. Okay, for some reason I rounded to 5 decimal digits in this table. Doesn't really matter. So we got this number, and then we got this. That's this guy. Just rounded to, giving more digits. And then we keep going, and you can see that it's getting closer and closer to 3, right? Over here we have 2.97472 and blah, blah, so on and so forth, right? And the error I've computed over here, right? So over here we have this error, over here we have this error, and this is what it is, right? All right. Now, let's talk about this last column that I added, which is the error divided by the previous error when we were halving, right? And so it's basically this error divided by this error, right? So we get this number, and so on, right? This number is this divided by this, right? That's what this is, right? Now, what that says is it's the ratio of the two errors, right? So it says, right, over here, because it's almost 0.5, it says that the error over here on the last line is about half the error on the previous, on the previous line, right? And so on, right? Over here, it's not quite a half, but you can see that it's sort of getting close to. I mean, maybe this is it's not quite a half over here, right? But by this line, it's quite close. They're all quite close to half. So it seems that whenever we halve the step size, halve the interval, we basically do twice the number of steps, right? So we halve the step size. What happens with the error is approximately, or it seems like the error will halve, right? So if we knew something about the error, we could figure out how many steps we need to take to get the error to be within something, right? So that's what's happening here. That's what this column is about, right? Now, that's because Euler's method is a so-called first-order method, right? So first-order method is that if you halve h, the error halves as well, right? It reduces by 1/2, by a factor of 1/2, right? So you multiply the error approximately, right? It's not quite right, and it doesn't always work. I mean, we already saw it here, right? I mean, it didn't, on the first couple of lines, it didn't quite, reduce by a factor of 1/2. But approximately, and eventually it sort of does. So where is this? What does the first mean? Well, if we had a second-order method, that would be a better method. It's basically, whenever you have h, when you double the number of steps, you multiply the error approximately by a factor of 1/4, which is 1/2 squared, right? And this 2 in the exponent, right? The square, that's the second, right? So, for example, if you had a fourth order method, there's a second order method in the exercises. There's also a first order method in the exercises, but I'll show it to you on the last slide. That's actually a very reasonable method that is used in practice sometimes. And the simplest one that is used in practice, and it's similar to Euler's method, and it's a fourth order method. So that means that each time you have the step size, the error goes down by a factor of 16, right? Which is 1/2 to the fourth, right? And that 4 is the fourth order method, right? All right. So we need to do. If we wanted to be within 0.1, we needed to do 64 steps with Euler, right? 64 computations of the new points, right? Now, if we want to, maybe we say, well, that's not good enough. We want to be within, 0.01. Well, with Euler, you really need to do another 2 to 3 halvings, right? So, approximately, something like 512 or 10,024 steps in our problem where we started. Now we started with already having 2 steps, and we were having from there, right? If you were starting with 1 step, just for simplicity, so it would be 10 halvings to get to 1024. Basically 1,000 steps, right? So if you with the first order method, maybe you would need to do 1,024 steps. Well, with the second order method, starting with approximately the same error, maybe, you really only need to do half as many halvings, right? You only need to do 5 halvings, right, to get the same reduction of error, right? Now, that might not seem like a big win, but it's a huge win, because if half as many halvings, because that's the number of halving, that's the thing in the exponent, right? So how many steps that's 32, right? So 32 versus 1024, that's a huge difference, right? If you were, if maybe well, I mean, a computer can easily do 1,000 steps. You're not going to notice 32 or 1,000 steps. But the thing is, you might be solving this ODE, for millions of different different parameters, right? And then it's then it's a big difference. Maybe to do one one iteration of some. You're trying to, I don't know, predict the weather or something, right? That's actually a very complicated differential equation, right? And the computation, takes a long time. And what they do is they fiddle with, maybe you're trying to figure out where a hurricane goes. So they fiddle with the parameters and run this model, but the model runs hours. Right now, if it runs, hours with 32 steps, then imagine how many times it's another 32 times that much to get to 1024. So if it took an hour to run one of these calculations with a second order method, it might take 32 hours with a first order method, right? That's a huge difference, right? Especially like maybe it doesn't take an hour, maybe it takes like maybe you have to run it a whole bunch of times, maybe it takes a day. Right, with a second order method, and it will take 32 days with a first order method, and by that time the hurricane is gone, right? So it's pointless then, right? And that was only a second order method. A fourth order method would even do more, because you'd need to do even half as many halvings as that, maybe 2 or 3 halvings, right? One halving would be 2 steps, 2 halvings would be 4 steps, right? 3 halvings would be 8 steps, but that's still a huge difference, 4 or 8 steps versus 1,000 steps, right? All right, so this can be a huge deal, especially when you need to run it a lot of times, or when your error really at the beginning is huge, right? And you need to do lots and lots of halvings for a first order method. All right. So in practice, the whole point is that you don't know what the error is, right? If you knew what the error is, you probably know the actual answer, right? And we don't know the actual answer. That's the whole point of what we're doing, right? I mean, in this simple example, we knew because we could actually solve this in closed form. But in general, in a real world application of this, we don't know what the answer is. So we don't know the error. We have to somehow estimate it without knowing the final answer. So let me, just give you sort of a basic idea of what you can do. A very simple version of what's actually being done. So basically, you do a whole bunch of halvings and you compute. You figure out the value for different halvings, right? Well, that's one thing that you can do. And then you could assume, so we're assuming Euler just for simplicity, right? Then you could assume that the error goes down by half, right? And so here's an exercise. It's just a little bit of algebra. So suppose you sort of look at this and you say, well, for simplicity, it seems like y at 2 is going to be bigger than all our approximation. So let's make that assumption for simplicity, right? And so suppose you don't know this. Of course, you don't know this. You're just going to assume that this is always approximately 1/2. What you could do is you could look at maybe these two values, and you don't know that the real answer is 3, right? So try to figure out, just by a little bit of algebra, what the error would be, right? approximately, right? And again, this is a very simplified, very sort of controlled environment. To do this, to do this sort of automatically, or or almost automatically, is much harder, right? But it's sort of like what what the computer is going to do if you try to ask it to compute, to give you a solution. Maybe you ask MATLAB to solve something numerically. All right, so that's an exercise. Now, of course, that's the trick in practice is to pick the right age, and you don't want to necessarily pick a really tiny age, because there's going to be lots of steps, but there are other problems with really tiny ages. So it's tricky, right? Anyway, so and we're gonna go through some of these some of these problems. Let's first get to a slightly different problem. So not maybe necessarily a problem of picking the right age, but maybe, what if we pick the wrong point to try to approximate? So if we approximate y3, right, with different step sizes, right, we keep getting these numbers, right, and they don't seem to be getting close to anything, right? I mean, definitely, it's not like it doesn't seem like we're having any error here, right? I mean, things just keep growing. Now, what's going on? Well, what's going on is that this equation, when you actually find the actual solution, y at 3 does not exist. There's actually there's an x minus 3 or 3 minus x in the denominator. So y at 3 is just not a thing, right? It doesn't exist, right? So as x gets closer and closer to 3, y actually goes to infinity in the real solution, right? Now, when you run the numerical algorithm, it gives you a number, right? You run it, you could say, well, I'm gonna get reasonably good approximation if I put let's say 0.0625 for h, right? So this would be a half, a quarter, an eighth, 16. So 1/16, maybe that's small enough. That's gonna always give me close enough. Well, I get 17. Well, 17 and infinity is very far, right? So we can't quite do that, right? We can't just stick in a small h and hope for the best, right? And here it's because it's infinity, but this actually might happen even if there is some finite number, some actual answer. Certain equations sometimes have this property that you're not quite getting the right answer until maybe like a very small h, right? So that can be a problem. This is a very simple version of that, right? When the actual guy is not defined, right? So but you're getting some numbers. It's just you get 17 and you think, well, okay, so the answer is 17. No. The answer is infinity. The answer doesn't exist really. So it's not 17, right? So you could get the wrong answer this way, right? Okay, so let's talk a little bit about the different issues, right? Again, it's picking the right age. That's the the other thing. It's also interpreting the answers, right? As we saw, right? There is no right age to figure out y at 3, because y at 3 doesn't exist, right? So you have to somehow figure out that no, it goes to infinity. Now in real applications, we don't really use Euler, but we use Runge-Kutta, let's say, and it's actually very close. And so fourth order, some fifth order methods. Usually, what what MATLAB, if I remember right, this was a while ago. This was like a decade ago. But what it used to do, and I don't know if it still does that, it would run a fifth order method, and then it would run the fourth order method, and then it would say, well, the fifth order method is much closer to the real answer than the fourth order method. So this, the difference is going to be very close to the error, right? That's the basic basic idea of what it's doing, right? And then it tries to choose the right age. Okay, so again, it's tricky, right? So first, computational time. You cannot just choose a really tiny age always, because it's going to take a long time to compute. I mean, plus the F might be difficult to evaluate. Now, one example where it's expensive to evaluate, I mean, maybe something in the function requires you to do some experiment. Right. So, for example, maybe some bit in the function is deflection of some part when you take a new Tesla, let's say, and you smash it against the wall, right? And that's going to be something in the function, right? You're changing x and y, and then to compute the f, you need to smash for two different x and y's, for one x and y, for two numbers x and y, you have to smash a Tesla, right? So each time you evaluate the function, you smash a Tesla. You don't want to smash too many Teslas against the wall; you're going to get fired, right? So, well, that would be an extreme example, but it could be something like this, right? The function might be hard to compute, expensive, or or slow, or you have to, maybe you have to do a whole bunch of computations, right? So, computational time is, could be an issue, right? You don't want things to take too long. Right, or how we said was the was the hurricane, right? If it takes you a month to figure out where the hurricane will be in 5 days, yeah, it's pointless. Okay, now the next thing is round of errors. So this is something that we haven't looked at, right? But computers don't really deal with exact numbers, right? I mean, generally, they deal with a number with a certain number of decimal, actually in binary, but let's say decimal digits, right? So they only have a certain number of significant digits that they can deal with, and everything else gets rounded off. So every computation that you're doing, you're rounding all the time inside. Now, each time you round and then you plug it in and you round again and you plug it in and you round again and plug it in and you round again. Well, all these errors add up, especially if it's, if it's sort of a complicated formula maybe, and you do it many times, it's, it adds up, and the round of error could lead to something really bad. So it might actually be that the errors that you're getting start getting worse as the age gets smaller and smaller. And so you have to also keep track of this. And this becomes much more complicated to do, because then you need to really know something about your F. All right, now another thing is stability. Certain equations can be so-called numerically unstable. That's what usually if you say, or stiff equations. Stiff problems. It's basically when the answers, even as you're maybe like halving the intervals or making the step size smaller and smaller, they don't seem to be getting closer to anything. That doesn't necessarily mean that maybe it goes off to infinity. Maybe you really just need a much smaller age, or it could mean a bunch of things, right? But it could be maybe the age that you need for a certain equation would be somewhere where you're getting these round-off errors that screw you up. And so you're just, maybe halving doesn't actually improve things, maybe it just makes it worse, right? So that sometimes happens. So maybe you need to, change the method, like get a different method that maybe, gets around that. Now, the worst thing is if you're, especially if you're letting the computer just do things automated. Now, most of the time, it's going to give you a reasonable answer, but every once in a while, it gives you an answer. It's going to be confident that that answer is the correct one, and it's going to be completely wrong, right? Because maybe this, this problem, maybe just by chance, you're actually, you're hitting numbers that seem to be close, but that's just by chance. If you picked a very different age, and maybe you weren't halving, but maybe you were going by thirds or something, then you would get numbers all over, right? So sometimes you might get bogus numbers, as if they were correct. So that's the worst case if there's no sort of warning of this, right? So sometimes the computer cannot tell that it cannot give you the right answer. Yeah, that's just what it is, right? And the more complicated the problem, the more common all of these problems are, right? So for simple ODEs, using something like Runge-Kutta that we're gonna look at next, it's most often it's pretty good. With a reasonable sized h, you're gonna get a reasonable answer. All right. So and one thing is that it's still a research topic. Maybe not so much for these methods for ODEs. It's a lot more for the numerical methods for PDEs. We're not going to really cover any more about numerical methods in this class. So this is just like a very short introduction. That this thing exists, but we're not really worried too much about numerical methods. That's a whole whole separate class. It's a lot more complicated. There's we're only interested in the theory of ODEs. All right. And so, this is still, numerical methods are, and they're going to be a research, current research topic for a long time, right? And especially as computers get faster and better, it's going to be possible to do certain things that we haven't done before. So there's new things to try, maybe. Right, and there's going to be sort of new ideas of how to solve certain equations that maybe we don't know how to solve now. All right, now, so here is, as I promised, the Runge-Kutta method, just so that it's not a big deal to sort of really memorize this at this point, right? But just so that you see how an actual method that's in application. How it looks. So again, we have the same sort of setup, right? So we have a step size and we have a initial value ODE, right? So the whole idea is the same, except each step is a little bit more complicated. So computing the next x is the same thing. You add h, right? But to compute the y, what you do is you compute the slope at 4 different points. That always depends on so you look at you basically you look at where would you go with Euler if the step was a half, right? And then where would you go with that new slope, and then you try to what would be the slope if you went forward with this third slope, right? So you get these 4 slopes, and let's not worry about why you do that. So you take these 4 slopes and you take this weighted average. So you basically average out, but you basically put more weight on the K2 and the K3. It puts twice as much weight. So it's basically like averaging out. It's you have K1 plus K2 plus K2 plus K3 plus K3 plus K4, right? So you really have 6 numbers. You're averaging those. That's what we're doing here. So you take that average. That's your slope. You go forward by that. That's your new y, right? So that's the Runge-Kutta method. It actually turns out that this is a 4th order method. So the error will go down by a factor of 16 whenever you have, approximately, right? So this is a very nice method. right? And it's fairly simple, right? I mean, it's, maybe not for doing by hand, but it's really easy to write a little computer software to run this. But of course, there's if you have MATLAB, there's these sort of things are written in there, so it will do that for you. All right, so I think that's good for this time. So all right.